Okay, because we are looking at design patterns, let me talk a little bit about a good design. Um, Typically, when you say you have a good design, it's when you think that your design feel just right. What I mean by just right is that it has a good level of abstraction. Like you see what you want to see, it's just enough details. It doesn't, you know, show you too many details. You don't feel like, okay, why do I need to see this to get things done? So it gives you just the right amount of information that you need, and it's flexible enough so that you can, you know, tune it, bend it to get what you want. So it shows you enough. It doesn't show you too many things, and it's flexible enough. But this description of a good design is kind of like very subjective, and it doesn't tell you much when how you're gonna get a good design. All right. So there are many criteria for a good design, a more objective one. But the goal for a good design for software modules or classes or whatever is that it should be your design and your software, the software that you have constructed based on a particular design should be easy to change, because always your software has to change, okay, because of some change in business, and some you need to adapt, or maybe the machine change, the technology change, the software has to adapt too. So it should be easy to change to change the software. Why how are you gonna get that goal is that you need to make sure that changes are localized, which means if there's one thing that has to be changed, then there should be a single place in your code that you should go to and just fix that part. Okay, but this is like an ideal situation. If you can do that, then you're really really good. But usually we're not gonna get to that exactly, but that's the goal. Okay, so like various concepts that help you to obtain to get this goal is called cohesion and coupling. Okay, um, I think you've seen I call the decouple before. It's the same thing. Okay, so cohesion means you want your system to have high cohesions. So cohesion talked about when things belong to the same group, it has to be really close to each other. Okay, if you put stuff here, okay, in the same module, right, they should come together nicely. Okay, close thing should be close. Okay, things that are grouped together has to be like close to each other. That's the high cohesion part. But you want low coupling. Okay, when things are in different places, okay, these two modules, they are in they are different modules. They should the dependency between these two modules should be small. So that's what we say low coupling. Okay, and when you have something that tightly connected and you want to break them down, you want to break them apart, you somehow need to destroy the coupling, or that's when we say decoupling. Okay, so these two concepts like cohesion and couplings is like the abstract concept that you can think of when you design classes and software and everything. Okay, but but if you work on object-oriented designs, this solid principle is somewhat more concrete. Okay, so this is solid. So there are 5 principles. S is single responsibility principle, which says that a class or a function or a unit of code should have exactly one responsibility. It shouldn't do too many things. It should do exactly one thing. Okay. The open close principle and the other principles, we look at that next time. But the Srp principle is probably the most important one, and when you look at things, you can always ask, is this function perform too many tasks? If that's the case, then you should split them up. Or maybe if it's perform just one task, does this function or does this method have the right name or something like that? So the Srp principle is very important. So that's the one that can be explained for this lecture. Okay, next lecture we will look at the other 4. Okay, all right. So let's see some concrete patterns. Okay, so this is called the command pattern. Okay, so basically so I'll come back to the description of the pattern later on, but it's like the idea for the command pattern is that okay, first of all, you should go ahead and read here the command patterns. So maybe you start with the Wikipedia article on the command pattern, read it for a little bit, and then go ahead to this game programming pattern website and read the command patterns. Okay, you should spend some time reading it and then come back and see the example that I would show you. Maybe read it for 5 minutes, or pause the video and then go read it for a few minutes. All right, I hope you read the description of the pattern for a little bit. Okay, so ideally the command pattern is when you wanna encapsulate the processing of something into an object so that you can deal with that later. Okay, the example of the core use of command is when you play a game and you can see like replay of the game. That's the result of the command patterns. Like think about it. Think about the banana, the monkey banana games. You hit some keyboard and the banana fly, right? And then that's it. How can you do the the replay of everything? That means you need to keep all the changes. Everything that change the state of the game should be kept. And how would you keep that? We keep it as a command object. Okay, so let me show you one example that demonstrate the usage of this pattern. Okay, the website show you many nice example of that, like when you have this input, but if you have a function associated with a particular button like this, then it's really hard to change the button mapping, right? But if you encapsulate each function as an object, now you can assign the particular command to a particular key. Then you can change the key mapping. So that's one example for the usage of the command patterns. Okay, so I'm gonna show you another one. Okay, so let me show you this example. So this is just the dot game, and then I change the dot so that let me run it again. Okay, so you have 10 dots, and they just, you know, I just simulate the physics, but if you hit the boundary, you bounce, and if you hit the left or right boundary, you bounce at the same speed. But if you hit the bottom, your speed drop by, you know, a few percentage. So you can see that, you know, the dot just jumping around a little bit. Okay, so it starts by jumping a lot, and then, you know, the jumps, it's the height keep decreasing. Okay, so the code is like this. So I have the update method as usual. Okay, so I actually update the location based on the speed, and I would update the speed with the gravity, and bounce, check if I hit the left wall or the bottom, and then I change the direction of the speed. Okay, so basically that, and then I have random speed, so that would give me a random initialization. Okay, now I would like to have a replay, or I would like to play the game backward. Okay, so the way to do that is that you would encapsulate. So if you recall, the command pattern is to encapsulate a request, or what you want to do with an object as an object. So here, what I would like to encapsulate is the update method. Okay, so typically the game loop would call the update for the dots. Okay, now I'm not gonna call it directly. Okay, I would encapsulate it as an object, and then I would call it later on. Okay, so the way I do it is the following. So if you look at the pattern like this, so instead of calling the action of the receiver directly, you call it through a command. Okay, a command would just call the action, and you can keep the command later on. And you can also with this, you can have a redo, and you can have you can undo stuff as well, because you would keep the command, and if you have a undo function of the command, you can, you know, you can have a list of commands that you have already applied, and then you can you know, undo steps. So previously it's really hard to have an undo, right? But with command pattern, you can do that, like undo and redo like this. So you have a list of commands, and then you can, you know, you can undo by, you know, moving backwards. Okay, so let me show you an example of that. Okay, first of all, I need to encapsulate the update as a command object. So let me call this rename this as function real update. Okay, if you run it, you can see that, you know, all the dots stay at the same place, because now its update function just doesn't do anything. Okay, so now I would encapsulate the command as a command object. So I create a class dot update command. Okay, and this command object would basically we gonna initialize it with the dot. Okay, so save dot, and then we create a function called execute that would perform this command. Okay, and since this command would encapsulate the call to real updates, we just call real update. Okay, so dot real update. Okay, so that's it. That's the dot update command. Okay. Now, instead of calling real update directly, we're not gonna call real update. Okay, we're gonna create the dot update command. Okay, so we're gonna do that. If you recall the game lib in the game loop, okay, it's called pre-update first, and then it called update on every element. And right now on the dots, the update method of the dots does nothing. Okay, and then it called render. So we would actually create a command object in pre-update and called it there instead of just calling the update here. Okay, so I would write on here pre-update. So commands is empty, and then for, so I would keep all the dots dot append dot. Okay, so I for each dot I would create a command object. So I would say command dot append dot update command, and I pass the dot to it. Okay, so now I have a list of commands, and then I can just execute it. So for C in command c.execute. Okay, so instead of just calling the update directly, we create a command and then we execute it. Okay, here. So now you should have the same functionality with the previous program now. Okay, so why do we do that? We don't get anything new, right? Okay, so let me show you how what you would gain from this. Okay, because now the update command has been, you know, reified. So reify means like you make something, a concept of something into a concrete something else. Okay, now you can keep these commands. Okay, so for each update I will keep all the commands, and then you can replay the command. First of all, you can play it backward. You can undo as well. So let's implement the undo operation here. So on the command I implement the undo method. Okay, so the way I would undo stuff is to do the following. So when I call execute, I would save the old state of the dot. So I would, because I know real update of the dot would just update x, vx, vy, and x and y, right? So I would just keep old state to be just keep all this, save the x. So dot equals save that dot. Okay, I would keep old state to be dot x dot y dot vx dot vy. I would keep all this old state there, and then I call undo. I would just basically update the xy and vxy of the dot back to the state that I have already saved. So I would say dot x dot y dot vx dot vy equal save dot old state. Okay, now my command has an undo function. So if you call an undo, your dot would move backward to the same previous step. Okay, and if you keep calling undo, you can play the dot, you know, jumping backward. Okay, so let me try to do that. Okay, so let me try to do that. So here in pre-update, I would need to save all the commands so that I can undo all the commands backward. Okay, so this is what I'm going to do. Save that command. Okay, and this is the new command, so let's call it the new command. Okay, so these are the list of the new commands, and then I would just save it. Append new command. Okay, so self.commands is the list of commands for each. So a command for each step is saved in commands. And then I would have self is reverse. Okay, so this is a flag that if I call is reverse, then it would go backward. Okay. So I would say self.is reverse equal true. So if I hit any key, then I would do the update backward by just calling undo. Okay, so let's fix this. Self.is reverse. Then self.reverse update. Okay, so let's write this reward update. Okay, so now I need to play the reverse back, the command backward. So I need some index on the current, the previous command, right? So I would keep the command index here. Index 0. So after I add a command, then I would say equals len -1. So that's the current index of the command. So I would basically do this. I would look at the command in the current index, and then I would just call the redo on all of that. So current command cell.commands dot cell.cmd index. So that's the current one, the previous one, right? And then so I would for C. In fact, if I want to do something complicated, I need to do the undo backward. So I would do the reverse commands, and then I would say call c.undo. Okay, and then I call self.cmd index -1. So I would go backward. So think about this image. Okay, I would go backward in time, right? So I decrease the command index, and if I run out of commands less than 0, then I would say cell.is reverse equal false, and I throw away all the commands that I have been saved. Okay, so this is the code. So let's try to run it and to see if it works. Okay, it's like that, and then if I hit any key, you can see that all my dots come back and just okay, so maybe my undo is broken somehow. Okay, it looks okay to go back, right? It would go back to the original point, and then when it reruns again, all the velocity go nuts. Okay, so but that's okay. So let me try to see why bad things happen like that. Oh, okay. I need to save Vx and Vy. Okay, so that's the bug. Okay, so let's run it again. Okay, you can see that I can go back and forth, right? So this is the power of command patterns, right? You can go backward. Okay, everything looks fine, right? This is like magic. Okay, Okay, so so that's an example of the command patterns. So but let's clean our code a little bit more. Okay, here is that we need to create the dot update command, right? So the game, oh, the Srp game need to know that you need this exact command, right, to do stuff. Now, if we have many kind of dots, then this code will be really bad, you know. So a pattern that you can use for this is to have a factory. So you want to create the command, the update command from the dot itself. So the dot itself knows exactly what the kind of command that it needs. So we would fix our code a little bit here. So let's say get update command in the dot. Okay, so we put this method in the dot itself, and then we would just return dot update command. So maybe the command may need something important, so you can put it here, exactly here. Okay, so instead of just create the command here, we just call dot get update command. Okay, so it's a little bit cleaner, and you can if your dot needs special kind of like commands depending on its states, then you can put it here. Okay, and this is a kind of like small creation method. Okay, so this is a method that create the update command. Okay, if you want to create stuff, there's another pattern called the factory pattern that I would show you maybe next time, or maybe during the lab section, that you can use as well. Okay, so so let me show you quickly the factory method patterns. So this is like you want to create stuff. Okay, you call instead of creating the stuff itself, you pass on the factory, and from that factory you create something from it. Okay, so that's how it works. Okay, we look at that soon. Okay, all right, so what else can you do with the command patterns? Okay, you can have a more complicated interaction between the dots, like when they're close to each other, you just bounce with each other, and that is a kind of update, and we can encapsulate that as another command. So let's do that quickly. But before that, let's this function is getting a little bit too long, right? So pre-update. So I would extract another function from it, another method. Okay. Let's call create update commands. So let's and then returns. Let's say new commands. Create update commands. Okay, it's a little bit shorter, and then execute it. Okay, and then we append and update the index. Okay, here you can even do this. You can replace this with list comprehension, but I'll leave it there for now. Okay. So the new command is just this update commands, and then I would like to have I would like to check if there are dots which are a little bit too close, and if they are too close, then I would create a new command that, you know, that ensure that they bounce with each other. Okay, so I would call check bounce. Okay, and this would create another set of commands as well. Okay, so I would browse command create. If that's the case, then I would just do that as well. So let's call this okay. So I would append both new command and browse command. Okay, so that's the commands that I would do. Okay, so now the browse command is something that I need to keep the I need to check all the dots and then represent how to browse between them, right? Okay, so I would create a dot browse command. So it should be dot one and dot two. Okay. So if that getting too close, then I would browse it. Okay, basically. So I would save the states dot one, dot two. Okay, so saving the state like this in the command looks like I have too many I need to I have this too many duplicate codes now, right? So I would let the dot save the state itself. So get state so that you can save it, right? So it would just return this xy and vxvy. And then I would say equals state. Okay, self dot, oh sorry, it should be self. Okay, so now I have get state and set state that can be used for undo and redo. So let's fix the dot update command first. Dot get state. Then I say dot set state. So dot o state. Okay. Okay, because I don't need the dot here, then I would just say self dot. Okay, self dot equals set state o state. Okay, so with that, let's see if everything still works. So let's comment the browse command thing for now. Okay, with the set state thing, then you should have everything. Okay, go back and forth. Okay, so that looks pretty nice, huh? Okay, so let's see. Okay, so let's implement the browse command now. So when I have two dots which are close, I would create the dot bounce command. Okay, so I would have all state 1 equals dot 1 dot get state self dot all state 2 get state, and then I would bounce the dot. Okay, so how would I bounce them? Okay, I would just basically let's do this. I would just let it move backward. Okay, so I would just say dot 1 dot vx dot 1 dot vx. Let's do that. Okay, let's switch the direction of the velocity, just that. Okay, and just that. Okay, to see if it, you know, it works or not. Okay, and then when I want to do the undo, I would basically do this. Dot 1 dot set state self dot all state 1, and same code here. Dot 2. All right, and finally I need to create a bunch of bounce state. Right, so create bounce check dot bounce. The name doesn't, so let's call create bounce commands. Okay, so dot d1 for d2 in self dots if d1 is not equal to d2. Okay, so I need to be sure that I'm not gonna check the bounce twice. So let's do this. Num the dots. So let's num dots. So I only look at the case when I is less than j. So d1 is self dots I, d2 self dots j. So if both dots are too close, then I would create the bounce command. Okay. See. Okay, so if they are too close, right? So I would say too close. Then appends dot d1 dot get bounce command with d2. Okay. So I would implement too close and get bounce command in the dot. So def is too close. Okay, so it's too close. Let's say is too close. Okay, so this time would be math.sqrt square root self.x minus dot x square, right, plus self.y minus dot y square. And then I would just call math dot square root, so import math. So let's do it directly, okay, and then return distance less than maybe 5. Then I would say it's too close, and then get bounce command, then return dot bounce command 7 dot. Okay, so let's see if it works. I would be pretty amazing if it works. Okay. Oh, num dots. Oh, okay, it's broken. It bounce command none type. Oh, I forget to return. Return. Okay, so let's run it again. Oh, okay. Okay. It crashed. Okay. So the bounce command doesn't have execute. Oh, execute. Okay, let's see it again. Oh, so this is the bad case when the bounce repeat. So I need to, when the dot get too close, I need to make it closer, maybe 2. Okay. So this is the bad case, but most of the time it works, right? Okay. So when 2 dots are too close, then it won't. This is pretty nice. It bounces, but then it's getting too close again, so I changed the direction of the velocity again, so you know you have an infinite loop there. Okay, to solve that, we need to when we do the bounce, so let me fix it here. We need to update the position as well, so let's say dot 1 dot x let's call dot 1 dot real update. After we update the distance, so it should work. Oh, so that's the dots have the same location, then oh, okay, when it bounces, you know, it's gonna get pretty crazy there, but we can play the reverse game, right? Okay, here. Okay, so okay, if you implement the bounce correctly, you can have many commands, and you can, you know, turn back time. Okay, so that's the command patterns. So this is like 2 dots having the same exact velocity. Okay, so there's 2 dots over there. Okay, all right, so I hope that this gives you some idea on how the command pattern works and how we would try to apply it. Okay, although the physics simulation is not that good, but I hope you can see why, you know, creating a commands allow you to do nice thing like playing the game backward. Okay, and if you save all this command, you can do the replay and everything from using this command patterns. All right, so in the next clip, I would see, we'll look at the state pattern, okay, and we conclude this lecture with this example of the pattern that you should avoid. This is singleton patterns, okay. All right, so let's see you in the next clip.